Next, we have Alejandro Soto, initial modeling of the atmospheric physics of a transient lunar atmosphere on the ancient moon.
Thank you. Something completely different. I want to start off real quick just saying, though, that this has been a fun, challenging little project that came about because, I do have a pointer. David Kring and Deborah Needham had done some work in predicting outgassing from volcanism and generating an atmosphere, and we're looking for someone to actually try to dive into some of the modeling of it. And the message got to me, and I got to play around with this project for a little bit. So it's been a nice little collaboration between our two survey groups. So the motivation is that, as I mentioned, Needham and Kring last year had a paper out discussing how a sequence of magma emplacement on the surface of the moon early on they were able to convert it into calculating some of the volume of those mare was created on the surface. From there, generated a production function of volatiles released over the lunar history, and we're able to basically to build a sequence of the volatile mass that's being outgassed by volcanism on the surface of the moon during its early years as a function of time. And what was really most interesting to me is that they were able to then convert this into an estimated atmospheric surface pressure, assuming that they generated a global atmosphere. And what's interesting about this is the kind of numbers they got. You can see here, and I hit the wrong button. You can see here at its peak, they are producing an estimated global surface pressure of around 900 Pascal, which is, a little bit bigger than Mars's current atmosphere, right? So now suddenly we're not talking about an exosphere, lunar atmosphere, we're talking about a collisional atmosphere where someone like me can come in and start applying some of my usual tools for understanding atmospheric dynamics to this type of object. Now, that's for a limited period in time. It's a transient atmosphere. It has other times where still even had 200 Pascal. But what's also interesting is even the sort of the lingering last remnants of this atmosphere as the magmatic activity died off, this is still in the tens of pascals, which is Pluto-like. And what we've discovered recently is the Pluto climate actually is more dynamic and interesting than many had thought originally. So there's some interesting comparisons to make here. What I wanted to do, I want to stop and say that these are often called transient atmospheres, at least from my perspective in the atmosphere community. There's not really a precise definition, agreed upon definition, but there's a range of things we think about with transient atmospheres, but usually it's a question of stability over time scale. So even something like Mars, and I did it again, even something like Mars over the right time scale, obliquity time scales and longer, can be considered transient. It probably underwent excursions where its atmosphere went almost completely away for a while and then came back. Io actually has interesting almost annual time scales driven by actual direct volcanic activity. And of course Pluto is another classic example of that. So for an early lunar atmosphere, there are a lot of things that we could tackle. There's a whole list. I sat down and started thinking of cool questions to go after, some of which Needham and Kring already started working on, like lifetime. Others, like photochemistry, is not an easy one to dive into, but would be interesting. But I decided for starters, just to go after something that I knew I could put in a controllable size and is sort of a little closer to my heart because I'm interested in large-scale dynamics. And so I wanted to understand what things in this atmosphere might have controlled the transport of atmospheric water vapor. This is all very initial preliminary work. It's all very at an idealized level, but I'm hoping that this helps start putting a framework of what this atmosphere might have looked like. The obvious comparison, I already mentioned once, is that if we look at the peak potential lunar atmosphere you had, a 900 Pascal atmosphere at its upper end, the obvious comparison is to Mars. But I'm going to make an argument here that from a dynamics perspective, due to some of the unique features of, well, not unique, but due to some of the features of the moon, orbital features, Titan may actually be a better representation of at least the atmospheric circulation structure. And so that's sort of where I'm going to go with this for today with the 12 minutes roughly I have. So, I wanted to emphasize, and the reason why Titan becomes more important is Mars has a one-day rotation period, very similar to what we have on Earth, which leads it to have circulation structure similar in many ways to Earth. Titan has a 16-day rotation period, which is much closer to what we see with the Moon. So one of the things, I'm not a lunar scientist by background. I got on this survey that I'm on, Project Espresso, because I'm doing instrumentation that we figured out we could do some cool stuff for asteroids. So I'm wandering into foreign lands here. And so I sort of just dug into some of the literature, trying to figure some of this out, and got some help from Bill Bakke on this. But trying to understand the history of the lunar orbit for the period that matters to us, this is sort of what I worked out, but if it's horribly wrong, please feel free to tell me. But since we're interested in atmospheric transport of water, vapor, and what kind of influence an early atmosphere might have had in putting water into the polar regions, I try to limit myself to the time frames after the Cassini transition, when the obliquity of the Moon settled down into now. And so from going through the literature, what it looks like is you have a lunar semi-major axis range of 30 to 60 Earth radii, is that period of time when things have settled out, where if you did put something in a polar cold trap, it might actually still be there. That translates into a lunar period of 10 to 30 Earth days, 30 being what we roughly have right now, and 10 might be the fastest that it rotated, but that being 10 times slower than Earth. And this is where it comes into play, where I'm arguing that the dynamical structure then is a little bit more like the regime of Titan, because Titan's at 15, 16 days, somewhere over here. So with that idea in mind, I decided to build up a simple general circulation model, an idealized one where I kept the number of knobs I had to play around with as simple as possible. The goal here was to build up an atmosphere that remained stable long enough so that I could look at what kind of structure would get built up. I assumed a global atmosphere. Not all the volcanic outgassing would have necessarily created a global transient atmosphere, but for right now, that's what I'm assuming. And I'm focusing on sort of the peak atmospheric case, and I put in the lunar gravity and radius. And then, of course, I'm now looking at those rotation rates. So let's see what this initial modeling has gotten me. So I'm going to slow down for a bit, because this is like a classic atmospheric circulation plot. But for those of you who are not used to reading these, what I'm plotting here, and we'll just focus on the top one, is latitude and then versus height. The height has been scaled for the pressure at any given level to the surface pressure. So you get 1 at the bottom of the atmosphere, 0 at the top of the atmosphere. What I'm also showing is a zonally averaged. I didn't assume any topography. I just kept things nice and simple, which means I can just take an average in the latitudinal direction and make things simple to plot up. And what you're seeing here is stream functions. So the atmosphere circulation would follow these lines. So you would rise up in the center and move poleward in this blue direction here for this northern cell. Going south, you would move poleward this way in this cell right here. And for this case of a one-day rotation period, you get an additional cell that goes in the reverse, conserving flux. So what I'm trying to make an argument here, though, is the top plot here, I wanted to show a one-day rotation period, but with the lunar gravity and lunar mass and lunar radius, and you get a sort of classic circulation structure. This is what Earth's circulation looks like. This is what Mars is on average looks like. Not exactly like this, but qualitatively. When we move to 10-day rotation period, which is, from my initial estimate, seems to be like the fastest the Moon would have been rotating over the period that I'm worried about, suddenly you now have the structure is completely different. You have just 2 cells, 1 in each hemisphere, driving transport. This pointer is not fun. Anyway, I'll just talk it out for people online or watching later. Now you just have 2 cells. Again, you still predominantly on an annual average have air rising in the equatorial region, and the upper levels moving poleward and coming back down. But now the air is coming back down in the poles. So any transport of a volatile, I don't care what volatile you want, now from this single circulation moves farther poleward than it would in a one-day rotational period. And we can move forward and actually even look at a 30-day rotation period, which is what the moon has right now. Basically, what you're seeing here is once you get what I'm showing here above 10-day rotation periods, you're in a different atmospheric structure than if you would be in a fast rate. This is a phenomenon we know about in the atmospheric community. The transition point from a 1-day rotation period to, say, 10, it depends on a lot of details of what you're modeling. And there's not a set theory that you can do this, estimate this ahead of time analytically, but it's consistent with what we know. And what's interesting to me then to start thinking about is, as I move forward and add more details to this models, what does this mean in terms of transporter volatiles? If we go back to the original figure 1 from Needham and Kring, there is a heterogeneous distribution of where the magma is coming out. So you have these source regions, but what I'm seeing here is within a hemisphere at least, these source regions should be able to well mix within that hemisphere. So equatorial outgassing should be able to reach into the polar region. What I don't know yet, because this is still initial modeling, as I said at the beginning, is sort of the amount of water vapor. If you produce X at the magma site, pump it into the atmosphere, what fraction of that X actually would make it into the polar region? You're going to get some rain out, some loss along the way. But this is sort of the start of trying to investigate and understand what that might mean. Ultimately, then, with some hope that whatever we find, we can eventually connect to the geology, which is where having this discussion here and presenting this with all of you is important, because I don't know the geology, and so I'll need the community's help with that. So that's it right now. I'm looking to develop more details into the dynamical model. Right now, I've sort of forced the radiation environment to sort of work. I want to get into more details in that, and I would like to do look at the photochemistry as well. A CO, I sort of blew past it earlier. I forgot to mention that it's a carbon monoxide, sulfur, hydrogen, and water are the predominant volatiles outgassed from the work from Needham and Kring. There's also going to be some really interesting photochemistry with that, because we see that happen on other planets, particularly with the sulfur has short lifetimes. What does it do? Where does it go? How does it affect the ultimate heating in the atmosphere, the stability? And then it'd be really interesting as it evolves and sort of dies out. You will move probably from a global to a regional atmosphere, like what you get on Io. How does that happen, and what does that mean for the sort of end stages of transport will be interesting. So that's what I'm up to right now. Thank you.
Okay, are there questions? OJ.
What boundary conditions did you use for the surface and for escape?
It's not explicitly modeling escape, because the time scales that I'm running on that was output from just a couple of years. For the surface boundary conditions, I think I'd have to go back and check. I think I started it at 250 or 260 Kelvin and just used like generic land albedo that we would use for Earth or something else. So it's probably actually a little too bright for the moon right now. And that's something I'm going to tune and lower down. One of the challenges of working with transient atmospheres is that you have to sort of start with a not completely realistic state and work it way down. If you just throw all the numbers in there, they tend to be unstable and crash. So to keep it simple, I just change the minimum number of things and try to look at primarily what rotation rate does to it. But I still need to work on getting the boundary conditions right. Yeah.
And you mentioned photochemistry a little bit. Did you consider the photo distraction of the water vapor, or that's?
No, I haven't done that yet, no. Needham and Kring had some initial estimates on atmospheric loss in their paper. I don't feel comfortable quoting the results, but they had predicted some lifetimes, which is how they got that evolution sort of pathway.
This is more of a philosophical question, but why does Mars still maintain its atmosphere? Shouldn't it have dissipated as well, like these atmospheres? I mean, I know you don't model that, but but why does Mars still retain it? Maybe the poles or something, still driven by the poles?
It's a good question. Why wouldn't this one? So it has to do with the atmospheric loss rate, and this is an area that I'm not good at, I'll be honest. So Maven's measuring what the actual loss rate is, But I'm not quite sure what aspect of loss at Mars's orbit is fundamentally different than at Earth that's driving that change.
Yeah, because it seems like the moon should be losing, the moon should have retained its atmosphere then, using
Yeah.
Mars as an analog.
David, I
No,
don't know
they're
if
really different.
you want to comment on that, or?
They're really different places.
Yeah.
Gravity and.
There's a climatologist modeler over there, and Tony at least is older.
Yeah, and that's a good point. I'm also forgetting gravity makes a big difference on loss rate.
Big.
Yeah.
Yeah, we have a question from Rick.
Yeah, what is the timescale for the meridional circulation to complete?
Yeah, I don't trust the timescale I've predicted so far. No, this is still, I started on this just a couple months ago. That's what I want to work out, what that is and how that compared to loss rates, because that would get to balancing what OJ is asking. If you have some water vapor coming out at somewhere in the mid-latitude out of a magma, what is that balance between transporting it to a polar region versus just stripping it off? I cannot quantitatively answer that yet. I guess my main point was to just to emphasize that that structurally it's actually not Mars-like, it's weirdly Titan-like. But trying to get those quantitative numbers is my next step.
Do you plan on putting the topography, or some topography in there, and in the sense that that may control some of the meridional flow and actually address potentially some of the longitudinal discrepancies in water abundances like we see on Mars?
I debated that. Certainly at the spatial scale, which is around 5 degrees that I'm working at, I don't think it actually matters. I'm not capturing that level of topography because it doesn't have extreme topography like Mars does, where, so.
I beg to differ.
Really?
The top of Cabeus to the bottom of Cabeus is 8 kilometers.
Over what, I need to go check to see if that's lost in the resolution I'm running at.
Right.
So possibly in the future at a higher resolution,
Yeah.
but I kind of feel like I need to nail some of the other physics first before I start doing that.
Of course.
Yeah, so I'm not saying it doesn't ever matter, I'm saying just at the scale I'm working at, I think it gets lost, yeah. Not because of the depth, but because of the horizontal,
Yeah.
yeah.
Okay,
All right, thank you.
Thank you.